So welcome, everybody. Thanks. Welcome. I know many of you, but I'm Christine Jones. I work here in the High Energy Division, and it's my pleasure today to introduce Dominik Riechers. He did his graduate work at the University of Heidelberg and Max Planck Institute for Astronomy, and he's now on the faculty at Cornell and actually drove here yesterday from Cornell. It's not an easy place to get to and from always. He describes himself, and this is a quote, as observationally driven astronomer who is occasionally distracted by attempts to model what he and others are observing. His primary focus has been on improving our understanding of the initial conditions for star formation in galaxies in the early universe, and also then understanding galaxy evolution over cosmic time. To accomplish these goals, Dominik measures the physical and chemical properties of the molecular gas in high redshift galaxies where stars and their planets are born, with the overall goal of understanding how the universe we observe today came to be. His research combines observations almost entirely across the spectrum from ALMA and the JVLA, as well as HST, Spitzer, for Giovanni, and Chandra. And today, his title is, I think, still, yes, The Intricate Role of Cold Gas and Dust in Galaxy Evolution at Early Cosmic Epochs. Thank you very much.
Yeah. Thank you, Christine. Yeah, so I'm going to talk a lot about observations of mostly gas and dust in galaxies in the early universe to try to understand really what they can tell us about galaxy evolution and why it's important to actually do this. And I'm going to be able to motivate to you why this is actually something that's interesting to do. So I'm doing this with a group of people, in particular focused on a large program that I'm leading at the Very Large Array, which is called Z, or the CO luminosity density at high redshift survey. I'm going to introduce what this is and what we can learn from it. And I especially want to emphasize my graduate student, Riccardo Pavesi, who has done much of the work that I'm going to show you in a paper that's about to come out. Okay, so why is this something that's interesting? And to really motivate this, we need to understand really what we know about galaxy evolution. And really one of the main things that we have learned, especially over the past 1.5 decades or so, is essentially how galaxies form stars and when they do so. And this has really helped us to understand how stellar mass builds up in the universe and how the universe can look the way that it looks at present day and all the galaxies that are in it. So in principle, the most general diagnostic that we look at and kind of which encaptures this in the broadest terms is the diagram that's shown here, which is often called the cosmic star formation history, or the volume density of star formation in galaxies as a function of redshift or as a function of look-back time. And this is something where we know that in the present day universe we essentially sit at this point, but then if you go out to high redshift to a look-back time of about 10 billion years or so, or a redshift of about 2, we see that there's essentially this steep increase going back from present day to this earlier point in time by a factor of about 10 to 30. So we see that there's a lot more star formation activity in the early universe than there is at present day. So for some reason, galaxies seem to form a lot more stars on average in the early universe. And this is also why this is often called the epoch of galaxy assembly, because about half the stellar mass that we see in galaxies at present day were formed at this earlier epoch. And then going back to early epochs, essentially we get this turnover here to the highest redshifts, all the way back to the first galaxies. There's not as many constraints here, and it's not as well constrained as at the lower redshifts, but in principle this is a shape that we know exists at present day, and this is kind of how galaxies form stars throughout cosmic times. However, there's a lot more that we can learn from this, and for example, one thing that we can do is we can take this integrated diagram and actually look at what kind of galaxies essentially contribute to this increase here, and that's what's shown in this panel here. So if I do a simple thing and split this up by infrared luminosity, which is a measure of dust-obscured star formation, and ask that compared to the total measurement here, what is the relative contribution from so-called lurks or luminous infrared galaxies, or U-lurks or ultraluminous infrared galaxies. And these U-lurks here are essentially galaxies that have infrared luminosities greater than about 10 to the 12 solar luminosities, which corresponds to star formation rates more than 100 solar masses per year. So in the nearby universe, these are the rare, most extremely star-forming galaxies that we know to exist. But kind of if you look at this integrated density, you see that actually at present day, their contribution to the total is almost negligible. So there's very few of these that contribute, and but there are also very few of them that exist. However, if you then go back to higher redshifts, you see that by redshift of 2 or so, these become the dominant contributors. So not only do we see enhanced star formation activity as a total, but it seems that there's more galaxies that have very high star formation rates at these earlier epochs. And of course, what we'd like to understand is why is this happening? And for a long time, the idea seemed to be like, well, in the nearby universe, the most extremely star-forming things are major mergers, so essentially train wrecks of galaxies. And by individual studies, especially at sub-millimeter wavelengths, which corresponds to the rest of infrared, at these high redshifts higher than 2 or so, essentially was found that there's this population of very intensely star-forming galaxies. They're called sub-millimeter galaxies based on the discovery wavelengths. But essentially, these are galaxies that have hundreds to thousands of solar mass per year star formation rates. And by studying them in detail, it was found that many of them actually do look like major mergers. And essentially, you could see some sort of merger sequence at these high redshifts that seem to be a scaled-up version of the reduced in the nearby universe. However, another thing that was recognized is that these things do exist, and they're kind of the tip of the star formation activity that goes on in the universe. But actually, there's too few of these very extreme events to really explain the overall increase. So again, the contribution of these very extreme systems, even at high redshift, is not dominant, and therefore it is not enough to really explain what's going on in the early universe. So what else is going on? So essentially, since the picture has been changed a little bit, and especially in the past 5 to 10 years, we have discovered this quantity that's shown here. Because what has been found, if you look at star-forming galaxies in the universe, and here I'm showing galaxies that are relatively nearby, and if you plot their star formation rate against their stellar mass, it seems that they follow a relation as shown here. That's the so-called star-forming main sequence. So it seems that most galaxies seem to form stars in a peculiar way, and if I tell you the stellar mass, you can tell me how much star formation is going on in these galaxies, and just for reference, what I'm showing here is where the Milky Way would sit on this relation. And this is really what most galaxies do, and this can you see based on the density of points here, but it's not, of course, all galaxies. There's, of course, also red and dead galaxies that, where star formation activity is ceased, and they sit below the main sequence. And then there's also some galaxies that sit above the main sequence. These are galaxies that we can call starbursts, and these are often associated with these very gas-rich major mergers, like I've shown you on the past slide. So these systems do exist, but by and large, they're much rarer than the general star-forming galaxy population. So this is what this looks like, but we can also look at this as a function of redshift to see if something that's true in the nearby universe actually exists at higher redshift. That's what's indicated here. So this is the same plot as in the last slide. What I'm showing you here is essentially higher redshift bins going out to a redshift of 2.5 or so. And we do see that this main sequence appears to exist out to high redshift. So essentially there's something that seems to be relatively universal. And these lines here just show you essentially the completeness limits. Another interesting thing is if you then take these and essentially overlay these fits to the main sequence here, what you get is this here. And what you see is that essentially going from redshift of 0 to redshift 2.5, you essentially see a continuous increase in the main sequence. So the main sequence does exist, but the star formation activity in galaxies increases, and therefore the offset of the main sequence goes to higher and higher levels. Okay, so if this main sequence exists, so kind of what kind of galaxies are there on the main sequence? So the first thing you can look at is, of course, just structural parameters, so in particular morphology, by doing high-resolution imaging, especially with the Hubble Space Telescope. What's shown here again in 3 panels is the same as in the last slide in 3 redshift bins, about 0, 1, and 2. But then what's indicated here as the color is essentially morphology of the galaxy. So kind of these colder and darker colors indicate morphologies that look like disk galaxies, and these kind of redder colors indicate galaxies that look like elliptical, so spheroidal galaxies. And what we can see is that these galaxies below the main sequence are typically look like spheroidals, but then on the main sequence out to the high redshift, essentially predominantly galaxies seem to look like disk galaxies, so not major mergers, not spheroidal galaxies, but they do look like disks. And there's something that you can also see by looking at the kinematics. So what's shown here is essentially a gas kinematic structure of some of these galaxies. And what we find is that from these kinematics, by fitting them, we find that at least half the galaxies on the main sequence appear to be large rotating disks rather than merging galaxies. So it seems that really merging is not the main thing that's responsible for this increase in star formation activity in the early universe. So the question is, what is really going on? Why is there this increase? And there's, of course, different things that can be happening. So the first possibility is that in principle, maybe the star formation process for some reason at high redshift is more efficient, and that's why essentially galaxies can simply form more stars than they can at present day. However, another possibility is simply that galaxies at high redshift might be more gas-rich than they are at present day. And the reason why this idea essentially came up is because we know that in the nearby universe there's this relation that's shown here that's often called the star formation law, or the molecular star formation law, or the Schmidt-Kennicut relation. So essentially, if you plot the surface density of star formation against the molecular gas surface density, essentially we see a strong relation between these two quantities. So in the nearby universe, essentially, if there's more molecular gas or higher gas surface density in galaxies essentially get more star formation activity. So there seems to be a close relation between these two, and therefore the interstellar medium or the gas seems to play an important role in star formation. And if something is going on at high redshift with the gas, this could also explain what we're seeing. So before I'm going to explain things in more detail, I want to first talk a bit about the tracers that we're going to use to essentially understand things in these high redshift galaxies. And this is just an illustration based on a model spectral energy distribution of a high redshift galaxy. And here I just picked a dusty galaxy because some of the features appear more pronounced. So what I'm showing here is just a spectral energy distribution going essentially from mid-infrared wavelengths all the way to the millimeter. And we see that there are several prominent features. And of course, the main prominent feature that we see here is this large bump that's essentially due to thermal dust emission. And this is essentially dust that's heated by young massive stars. Essentially, they emit a lot of UV photons, which then get absorbed by the dust and re-emitted as thermal emission in the rest frame far infrared. So essentially, the far infrared emission that we see in this bump here due to thermal dust emission, in this sense, is a measure of star formation rate because it tells you how many young massive stars there are that contribute to the dust heating. So it tells us something about recent star formation, and therefore commonly is used as a tracer of the star formation rate. Then you see several features. So, for example, at the shorter wavelength, there's this PARs or polycyclic aromatic hydrocarbons, which are features in the dust. And this is something that, of course, we've studied very prominently with Spitzer. Out to redshift of 4 is where we got with Spitzer in studying this. And this is something that will also be very important and unique to study with JWST when it comes online at higher resolution and better sensitivity than Spitzer could deliver at the time. This is going to tell us both about the star formation properties and the properties of the dust itself by doing these studies in a lot of detail. I'm not going to talk about this further today. Instead, the diagnostics that I'm going to talk mostly about are these other features that I haven't mentioned yet. And these are most prominently here, these spectral lines, which are the rotational ladder of carbon monoxide or the CO molecule, CO1 to 0, 2 to 1, and higher transitions that come up from the millimeter all the way to the far infrared. And essentially, these CO lines are the main tracer that we're using to trace molecular gas in galaxies. And they tell us about the amount of gas that's there, so the gas masses. But then also by studying multiple lines, we can look at the excitation of the gas to learn something about the physical properties. And by imaging it, looking at the gas dynamics, we can also learn more about what's driving what's going on in these galaxies. So there's a lot of things that we can learn from studying these CO lines. And then in addition to the CO lines, there's these prominent features here in the far infrared on top of the SAD. And these are atomic fine structure lines from carbon, nitrogen, and oxygen. So the first order, these are cooling lines of the interstellar medium. And these are going to be more important in the second part of my talk when we're trying to understand some properties that we cannot understand with other tracers very nicely in the early universe. But in general, these are the tracers that we are talking about. And this here is just a model, but just to give you an impression that this is also what you can do in high redshift, and that actually it's more complicated than that. So here's just an example of a measurement that we did, and since it was a very exciting galaxy found very far away, we could actually do a very detailed study. And this here is showing you the same as in the SAD figure, just flipped around this axis here because I'm showing frequency instead of wavelength. So what we're seeing sloping up here in yellow is essentially this dust continuum emission. But then you see all of these discrete features actually on top of the continuum. For reference, what I'm showing you here is a nearby starburst galaxy where you can see the same kind of features popping up in different molecules. So we can see that there's very rich information about the interstellar medium and captured in these spectra at long wavelengths. In principle, there's a lot of information out there. But what I'm going to concentrate on in the following is essentially just these CO lines here, which are typically the brightest ones and the ones that are the best calibrated tracers of gas properties. So what can we do with this? So we've already touched upon the star formation law, and in principle, this is of course something that we ideally want to do out to high redshift. And what I'm showing you here is essentially the simplest version of this that you can do by looking at observables. So in principle, what we want to have plotted up on one axis here is some proxy for the gas mass, or the molecular gas mass in particular, in galaxies. And as I've just indicated, I'm going to use the CO luminosity as a proxy for the gas mass. And then on this axis here, I want some proxy for the star formation rate, and I'm going to use here the far infrared luminosity that we're having, that we've seen is associated with the dust heating from young massive stars. So if you do this, essentially these nearby galaxies that I've shown you on the previous plot are down here. But then if you look at these main sequence galaxies at high redshift, essentially the points are found here, and you can see that indeed they seem to follow a relation between these two properties relatively clearly. Of course, these are not all galaxies. We can also look at the other galaxy populations, in particular these starburst or merger-driven systems. And we typically see that they seem to sit a bit higher in this diagram, so you get more star formation activity per unit gas mass. So there seems to be some sort of higher efficiency of star formation in these systems that can be related to merging activity. And some people have proposed that there might be two sequences based on the mode of star formation, merger-driven or more secular. Also, what's commonly shown is essentially that this is maybe a nonlinear relation with a larger scatter. I'm not going to argue one direction or the other because there's different opinions out there, but I think the general trend that we're seeing is that there's a clear relation between these two properties. However, the other thing that we're also seeing is that these colored points, again, here are the high redshift points with the high star formation activity. What we see is that they do sit high on essentially both of the axes. So indeed, these more highly star-forming galaxies at high redshift seem to have higher interstellar medium gas content. And therefore, it seems to be conceivable that essentially this increased star formation activity is mostly or maybe even entirely driven by an enhanced interstellar medium content and interstellar medium properties. And therefore, looking at this gas is important to understand what's really going on. Another way to look at this is what's shown here. So instead of looking at total quantities, we can look at something like the gas fraction. So what I'm showing here is just the ratio between gas mass and stellar mass, which is one way of expressing this as a function of redshift. And what we are seeing is that, again, here is redshift 0 at present day. Going on to a high redshift, there's a clear increase in the gas fraction in galaxies, which again argues for galaxies having a higher gas content, and this being the main driver of the increased star formation activity that we're seeing. So we don't need to introduce drastically different physical properties at high redshift to explain what's going on, but really can understand this by galaxies having more gas and accreting more gas at this higher redshift to essentially maintain this higher star formation activity. Okay, if this is the case, then of course to understand the origin and shape of the star formation history. Is it okay? I'm good. Great. So essentially understand the origin of the shape of the star formation history. In principle, if the interstellar medium is what's driving it, what we ideally want to understand complementary to this is the plot that's shown here, which is essentially the volume density of molecular gas in galaxies as a function of redshift. Because essentially this together will then tell us how galaxies and maybe why galaxies form more stars at high redshift and why kind of you get this peculiar shape out for the star formation history. And of course, in principle, if something like the star formation law exists, we know what this quantity here looks like because we can just invert the star formation law and project it over here and we can make some predictions for what this should look like. However, the problem with the star formation law is first what we've seen is that there's actually conceivable scatter, and this scatter is probably intrinsic. It's not only due to the quality of the measurements. So essentially, it's not a simple one-to-one relation that we're looking at, but something that entails complicated physics. However, the other problem is also that these galaxies that we have so far observed in molecular gas at high redshift are highly selected populations. So we look at things that are bright in the infrared, things that are bright in the radio, things that are bright in the UV, things that have certain colors in the optical and the infrared. So essentially these are specific galaxy populations for which we know these properties, but kind of inverting this and asking how much gas is out there, we cannot really do this because we know if this really captures all of the gas that's out there in galaxies at high redshifts. So essentially what we want to do in addition to complement these observations that exist at the moment is to essentially invert the measurement and instead of selecting galaxies and other wavelengths, essentially select them directly through their gas content. So essentially try to do measurements at high redshift based on the gas content and then looking at what kind of galaxies these are. And this is something that we started trying to do in something we can call a molecular deep field. So essentially you do a volume scan for molecular line emission in galaxies at high redshift. So this is kind of the idea behind this survey that we're doing. And for the context, we've started doing this with a pilot survey a while ago, but so far we have essentially initiated 3 different programs. The first one we did, this pilot, was with the Iran Plateau de Boer interferometer at 3-meter wavelength in the Hubble Deep Field North. But then the 2 main surveys that we're carrying out at the moment are being done with the VLA and the ALMA telescopes. And the VLA survey is what I'm going to talk about today because this is the one that I'm leading. That's the Cold Z survey. And then this survey on ALMA, and this is done in the Cosmos and Goods North extragalactic survey field. So there's a lot of ancillary data at other wavelengths for the galaxies that we detect. And the survey with ALMA is being done in the Hubble Ultra Deep Field in the south, led by Fabian Walter and Manuel Aravena initially for the pilot. And this has now been extended in cycle 4 to a large program. So the specific difference between these 2 surveys is that first the VLA survey goes over a larger area. So it's about an area of 60 arcminutes squared, which to some of you might not sound like a lot, but actually it's about 2 orders of magnitude larger than the pilot that we did, which only took a few hundred hours with the Plateau de Boer. And essentially that we're specifically targeting the CO1 to 0 line at redshifts between 2 and 3. And the reason why targeting the CO1 to 0 line is important is that this is a ground state rotational transition. We can also observe other rotational transitions, but the relative strength of the higher J transitions compared to the ground state transition depends on the actual physical properties of the galaxies and therefore the gas excitation. And we know that there's a fair scatter between the gas excitation that we see between different galaxy populations. So ideally, we want to do this measurement in the ground state line, which is least affected by this excitation effect. And this is actually also what's best calibrated towards gas masses in the local universe. So these are the two unique components that we have for the VLA survey. And then the advantage with ALMA, of course, is that ALMA is extremely sensitive. So the ALMA survey targets higher J lines, but it's essentially it's the deepest of the surveys that we are carrying out. And the other nice thing is that because we are doing shorter wavelengths, we also find other interesting lines. For example, the carbon plus line, we also capture at very high redshifts, which might be detectable. And this is another component to the surveys being done with ALMA. However, again, today I'm going to concentrate here on the VLA survey, but the survey strategies are similar between the two. So what is the measurement that we're trying to do? So essentially, we want to measure the gas content in galaxies at high redshifts. And the measurement that we do directly is CO emission. And the measurement that you can do by doing these blind volume scans essentially is to measure a luminosity function. And that's what's shown here. So essentially we measure the CO luminosity function at different redshifts. And what I'm showing you here is essentially what it looks like in the nearby universe at redshift 0. This is the data, and then overplotted are some models. So at redshift 0, we have a measurement of the luminosity function in CO. But at high redshift, we really don't have that because, again, we selected galaxies. So we just had a very incomplete view of this before doing this kind of more blind selections. But what we're trying to do here is essentially do this measurement redshift between redshifts 2 and 3 and CO1 to 0. But then at the same wavelength, we also get the CO2 to 1 line between redshifts of 5 to 7 or so. But we also get some constraints. And what I'm showing here is just the different model predictions that exist. Then once we've measured the luminosity function, essentially we just integrate over the luminosity function to get the total gas content out. And then we can essentially place constraints on this gas density plot here to see where we come out relative to the expectations and what this might tell us about what's going on in these galaxies. So again, this is something we do with the VLA, and these are results that I'm mostly showing you from my graduate student, Riccardo Pavesi, that came out of this survey. So what do the data look like, and what kind of data do we have? So again, in this field, we targeted 2 regions, and the first field that we targeted is in the Cosmos survey field, and this essentially is doing a deeper area. It's essentially doing a deeper area, but essentially a smaller region on this sky to essentially constrain the faint end. What I'm showing here is just the continuum map that we get out at these wavelengths from the VLA data. And the region that we selected essentially is this region shown here in the visible. And we selected this because we knew that there's one galaxy here at redshift 5.3 that we should detect in the CO2 to 1 line that we can then use to essentially calibrate our search methods, which is something that hasn't really been done before in this fashion with interferometric data. So essentially this is one of the reasons why we selected this particular region, and we did a 7-pointing mosaic with the VLA, which is what you're seeing here. And you see that there's several continuum sources, and in principle these yellow dots that I'm showing you are the sources or the candidates that we found. And in addition to that, we did a second field in the Goods North Canals region, which is a much larger mosaic, but about a factor of 3 shallower than this here to essentially cover the bright end of the luminosity function. And just what I'm showing you here to scale is this emission field that we've done with the Plateau de Bure to give you an impression that this is really a much larger area than has been tried so far, and therefore that we get much more reliable constraints that have been done in the past. So for those of you that are familiar with this field, so this year what I'm showing you here is essentially the exposure map from candles in the with 3 bands from Hubble. So what we specifically targeted is this region here where we have the deepest near-infrared HST data and therefore particularly good constraints in this field. So this is what we targeted. Okay, then again, what we targeted is the CO1 to 0 line between redshifts 2 and 3. So what I'm showing you here is the observed frequency that we used versus the redshift of line emission, and then these lines here show you how the different CO lines redshift through this window. And then kind of these yellow regions here show the frequencies that we selected for the 2 fields that are being covered. So again, we're selecting specifically CO1 to 0 between redshifts 1.9 and 2.8, and we get CO2 to 1 between redshifts 4.9 and 6.7. And in total, the survey volume covers about 400,000 cubic megaparsec on the sky with the setup, and this is just a single tuning, essentially with the VLA that we're doing. So the other important question is, of course, the sensitivity limits that we're reaching, and that's what's shown in this plot. So what I'm showing you here is the CO luminosity sensitivity that we have, again, as a function of redshift in the survey. This here is the bright field, and this here is the deeper field. And for comparison, what these dots up on here are galaxies that have been previously detected in CO emission at this particular redshifts, and essentially this is from a review article by Carilli and Walter. And what you see here is that kind of the more modestly deep of the fields would essentially detect most of these galaxies that have been previously detected, and the deeper region essentially is deeper than anything that has been detected before. So it's essentially well suited to complement these targeted studies that have been done previously in terms of the sensitivity that we achieve. Okay, so the next thing that I'm going to do is I'm going to spare you the details of how we actually did the selection, because there's a lot of kind of try and error involved in different techniques that we tried, a lot of statistics to make sure that what we get out makes sense. I'm jumping straight to the point where I'm showing you some of the candidates. And here's just a few examples of them. So what I'm showing you always in the left panel here is the CO contours overlaid on an HST I-band image. And here's the CO contours overlaid on IREX 3.6 micron image. And here's the CO spectra that we get. So here's just 8 examples of them, and in total we found 58 candidate CO emitters in this survey volume, about equal numbers in each of the two fields. Of course, because of the shape of the luminosity function, in the deeper field we pick up a similar amount because there's a lot more fainter sources and brighter sources. So one thing that we want to emphasize is that these are candidates because a lot of them are not confirmed. However, we have independently confirmed 7 of the 58 sources through other CO lines. And actually we find that 3 of them are redshift higher than 5. And this includes the one source that we knew would be there by selection in one of the fields. However, then if you look at other wavelengths, essentially we see that a little bit more than half of them have candidates for counterparts at optical or infrared wavelengths. And this is really why I want to emphasize the candidate aspect. We do know of some galaxies that are real among these 7 that do not have a counterpart at optical infrared wavelengths. So we know that there's real candidates without counterparts. But since there's a large number of them, we only treat these statistics as candidates as long as they're not independently confirmed. So this is just for the context. We use them in statistical studies, but they're considered candidates for the most part. Then the CO fluxes that we get cover a dynamic range of about a factor of 50 or so, and we get more than an order of magnitude variation in the line width that we measure among these candidates. Nor you get a bit of an impression of that here, that the line profiles can be very different. And this is also one of the challenges that we had to go through in verifying and validating our selection techniques. Okay, so these are individual candidates, but of course, since we target extragalactic deep fields, there's more information in there. And another thing that we can do is, instead of selecting things directly, we can also then, once we have this data, go to sources that we know have spectroscopic redshifts at other wavelengths, and then just stack them up to see if we can get any signal for galaxies without individual detections. And in the Goods North field, essentially we have of order 70 spectroscopic redshifts with high quality, that are not individually detected, and indeed if you stack the signal we get kind of a faint signal. It's about 3.7 sigma, so it's tentative. It's not a very firm detection, but if you go through and measure the flux and then look at the ancillary properties like the stellar mass and star formation rates for these galaxies that go into the stack, essentially the strength of the signal that you get out is consistent with what you would expect from the star formation law. So it's conceivable that is a real signal, even though the significance at this point is limited. Of course, we got excited when this happened, so essentially we tried more of this. In particular, one thing that we turned to is the 3D HST survey, which is a GRISM survey that has been carried out to measure more and more redshifts. And essentially there we have about 700 redshifts in this volume. But it turned out if you stack all of them, there's no detection. And also if you only take the best 10 to 20% of the GRISM redshifts, we do not obtain a detection. But in principle, that's something that's actually anticipated, and this is related to the fact that the precision of these redshifts is limited to a few hundred kilometers a second. So what essentially happens is that in the stacking you end up washing out the signal, so the signal gets distributed around, and this is why it's not as easy to detect. So we really need very precise spectroscopic redshifts to do this successfully with the sample size that we have at the moment. So essentially we only set a limit on this stack based on the GRISM redshifts. And then what I'm not going to show, but just mention, is that also there's some tentative 4 to 5 sigma detections for individual sources that exist within this volume. So at this signal to noise, we do not consider them for a statistical sample, but it seems pretty clear that there's more information in the survey. Okay, so these are just the candidates, but of course the main measurement we want to do is the luminosity function and then the gas density of the universe. And just for context, what I'm showing you here is the constraints that we got from these 2 previous pilot surveys. So here's just the luminosity function, and then these lines here are different model predictions that existed for what it should look like at these redshifts. And then the boxes here show the constraints that we had previously at a redshift of about 2.5 from these pilot surveys on relatively small areas. So what I'm showing you here is then the information that we get from our new survey from this larger area. In the different colors here are the cosmos and Gold's North fields, so the two different fields. And you see what you expect, that for the shallower field that's larger, you get better constraints on the bright end, and for the deeper field you get deeper constraints on the faint end. But this is the overall constraints that we get out. And the nice thing is that between these two independent fields, the measurement seems to come out consistent, and therefore we decide to essentially merge the information from both fields to come out with these constraints here, shown in the boxes. And indeed, what we can see is that there's a clear shape to the luminosity function, and therefore that for the first time we actually seem to be able to measure the near move of the luminosity function at these high redshifts of about 2.5 or so. And the second thing, and we see that the knee is essentially at this relatively high position here. And the second thing that's obviously interesting is that you can compare this to the model predictions, and you can see that these two models here are clearly not supported by the data. It's only this third one here that comes somewhat close to what's seen in the data, and it's probably consistent within the real uncertainties with the data to first order. So what are these models? So this model here is essentially just if you take the infrared constraints that have been obtained with Herschel and just apply the star formation law and invert it, essentially this constraint that you get, and this comes out close. But essentially these two models here are based on semi-analytical models, and you can see that they come out wrong to first order. And the question is, why is this really? And I can't say that we fully understood it, but one of the reasons that we think is connected to this is that if you look at the simulations in more detail, actually they're not particularly good at the moment, at least, to fully predict the main sequence at these redshifts. So what I'm showing here is essentially a compilation from the Somerville and DeVay review article. Again, the main sequence at different redshifts, and the lines here are the different kinds of model predictions that existed at the time. And you can see that here at this redshift of 1 and 2, that the predictions of the main sequence come out below the data. So essentially that it predicts lower star formation rates than are observed. And this would be at least partially a reason to understand why it would be predicted that they also have less gas content in them when once kind of the star formation was considered. So this probably plays a role, but it's not fully understood at this point, I would say, why they are off beyond the fact that they don't fully recover the main sequence. So I think there's a lot more work to be done to really fully understand the reason for it. However, then what we can do is, as I indicated, we can just integrate over the luminosity function and see what constraint we get. And again, the colored boxes here are the constraints from the pilots. And since this pilot surveys targeted higher JCO lines, there's a lot more of these CO lines that get redshifted through the observing window. And that's why they set constraints over a broader range in redshift, but essentially with larger uncertainties in each redshift bin. And then what we have here overplotted in blue is the constraint that we get from the VLA survey. And we do see that's consistent with these other two fields, that the pilot fields have been done, but again, with smaller uncertainties than we could do before. So it really seems that we can set a good constraint on the gas density doing this measurement. But the other interesting thing is that, again, if you turn to the models and see how they compare to the actual measurement, you see that kind of the integrated measurement actually comes out consistent with the expectation. So in those terms, essentially, if you integrate over the luminosity function, the total amount of gas that's predicted to be there seems to be close to reality. It's just the shape of the luminosity function that appears to be quite different from what was expected. Okay, so we can see that we can place constraints, and the uncertainties are still considerable, but we can see that there seems to be a trend towards a decreasing gas density to the lower redshift, and again, then it's increased to about a redshift of 2 or so. So it comes out comparable to what you expect, but for the first time now, we actually do have a measurement that's relatively reliable that we can use to essentially understand things better. Another interesting thing is that if you look at these very high redshifts here, there seems to be an indication, a possible indication for a downturn. But again, the data is not quite good enough yet to really do this. And then we have to deal with these large uncertainties overall. So it's not 100% straightforward to come out with a unique model that can describe things, because there's still these uncertainties. But I think it's a good proof of concept that this actually works, and that we can set considerable constraints on this quantity. So, of course, to do this better, what we need to first order is more data. We want to do larger fields, maybe also go a bit deeper to constrain the faint end better. And this is something that we're certainly going to do, but also something, or probably the main reason why I'm very excited about a conceptual study that's going on at the moment, and that's going to be submitted for the US Decadal Survey, the 2020 survey, which is something that we call the NGVLA, or the Next Generation Very Large Array. And essentially, in a nutshell, what this is just is a telescope that's similar to the Very Large Array, but it's essentially a factor of 10 more effective collecting area and a factor of 10 higher resolution, and it also does have a higher frequency coverage. So essentially, because of the greater sensitivity, this will be an instrument that will be ideally suited to do these measurements very precisely. So kind of the green boxes here show kind of some predictions that have been made for what the NGV will be able to do in a survey that is not an outrageous amount of time. So really, once we have this observatory, we should be able to do very precise measurements, hopefully do a lot of improvements in the meantime. But this is one of the reasons why I'm excited and why this is essentially one of the main science goals that has been proposed for this planned observatory. And I'm happy to talk more about this after the talk if anybody's interested. Okay, so this is kind of what has been done, and we've seen that there's these possibly interesting trends going on to higher redshifts, but actually going on to the higher redshifts, it's might be a bit more difficult to actually get good measurements out from doing CO studies. And of course, galaxies have been detected in CO emission out to much higher redshifts. I'm showing here again an example of redshift of 6 or so that we've recently found with ALMA. But again, it's one of these major mergers, one of these galaxies that are very dusty, that are probably the tip of the luminosity function. And these things are highly enriched already at high redshifts, so we can measure them relatively straightforwardly in CO emission. However, there's strong signs that this is maybe not true for more modest, more normal galaxies as we go out to high and higher redshift. And one of the examples of this is what's shown here, this from a paper of Reinhard Genzel. So what's shown here is two galaxies between redshifts of 2 and 3 that are on the main sequence and that have similar star formation rates, sizes, and dynamical masses. And what I'm showing you in red here is essentially the H-alpha spectra, which in these cases is used as an indicator for the star formation rate. And then what's overplotted in blue is the corresponding CO emission that we get from these galaxies. And I can see that there's a drastic emission in the strength of the CO line between these two galaxies with similar star formation rates. And the question is, why is this happening and what's going on? And what we think is happening is that something is changing in the molecular gas properties that makes CO not as ideal a tracer of the molecular gas in galaxies, and that this is probably due to metallicity. And the way that this is captured is something that we call the alpha CO conversion factor, and this is essentially where a lot of the dirty work is hidden that happens in this field always, because the conversion factor essentially takes the CO flux or CO luminosity of a galaxy and is used to then infer a gas mass from that. And we have a fairly good understanding for how this looks like in normal galaxies and also in starbursts in the nearby universe, and certain galaxies at high redshift, and we do see that there's kind of a change in this depending on the exact galaxy properties. However, something that has also been indications have also been found for is that this alpha CO conversion factor actually scales with metallicity. So essentially you see this trend here with metallicity. So as you go to lower and lower metallicity, essentially CO becomes worse and worse at actually tracing the H2 gas, which is most of the molecular gas that we see in galaxies. And a lot of it is what some people, although I don't like that term in particular, call CO dark, because of the change in gas properties at lower metallicities. So this is something that's interesting and of course that we're trying to understand, but it also is something that is a bit worrisome if you go out to a higher and higher redshift in terms of trying to understand and study the interstellar medium properties of galaxies out to the highest redshifts. So essentially the way that we're trying to work around this is that if this is going on, that for these galaxies where we expect it to be happening, that we try to use different tracers and try to understand based on these different tracers the interstellar medium properties in these other kinds of galaxies. In particular, the lines that we like to use are these fine structure lines of carbon, nitrogen, and oxygen that I've already mentioned near the beginning. Because these are lines that scale much less strong with metallicity, so they're still relatively bright in low metallicity galaxies. And the other nice thing is that they actually become redshifted through the observing bands of ALMA over large ranges in redshift, so we can actually use them as diagnostics from the ground at high redshift, even though they can only be accessed from space for the most part at a redshift of 0. And the most prominent line that's most commonly used at the moment is this line from Carbon Plus here at 158 micron, which is mostly a tracer of PDRs of photon-dominated regions and partially also of H2 regions. So the first measurements that we did at high redshift with ALMA is in this line here. And why is this a particularly interesting line? Well, it's to first order interesting because it is a very bright line. And for example, in galaxies like the Milky Way, it makes up about 0.3% of the far-infrared luminosity, the entire far-infrared luminosity of the Milky Way. And that's true for many relatively normal star-forming galaxies. In particular, if you compare galaxies of different star formation activity, going from the most extreme starburst to more modest systems. Essentially, the line compared to the continuum emission becomes more increasingly strong as you go to more and more modest systems. So this is a line that's particularly useful for studies of galaxies that are not extreme, that are relatively modest, and this is why it's a good choice, apart from the fact that it gets redshift to a wavelength that we can observe and image from the ground. So once ALMA came online, we started trying to do this, and we went after normal or main sequence galaxies between redshifts of 5 and 6. And this here is the first galaxy that we tried, and where we gained a successful detection, and you can see that actually it's nicely resolved. So we also get some velocity information from this measurement. And this was a relatively short integration with only a third of the array very early on. So based on this, we then went back and did a larger sample of about 10 galaxies, and we detected all of them in the C+ emission line. And these are really, again, normal galaxies selected through the line break technique. And normal galaxies at these redshifts means that they're essentially close to L star UV luminosities. And then some of them we detect the dust emissions. We can infer both the dust unobscured star formation rates from the UV and the dust obscured ones from the infrared. And we find that these have star formation rates between about 20 and about 150 to 200 solar masses per year. So these are much more modest than these extreme starbursts that we've traditionally studied at these wavelengths. Because this has been so successful, we essentially also got a large program in the current cycle, which is called the Alpine program, where we extend this to 120 galaxies between redshifts of 4 and 6. So this essentially is a nice demonstration that we do have a diagnostic that we can use relatively routinely with something like ALMA to study the interstellar medium in high redshift galaxies. But since it's a different tracer, we also need to understand what we can actually learn from these lines. Kind of the simplest thing that we can look at is what's shown here in this relation. So essentially what we can plot is the ratio between the C+ line luminosity and the infrared luminosity. And again, the infrared luminosity is here, this tracer of dust obscured star formation, and plotted against the infrared luminosity. And what we see here as a black dots essentially is what we find in the local universe, and there's always been the indication of this trend here in the nearby universe that there's a decrease towards more infrared luminous systems. So if we go to this merger-driven starburst, the relative strength of the C+ line becomes lower, and that's what I've already indicated 2 slides ago, that for very extreme systems there's things that there are processes going on that suppress the strength of this line. But then essentially for these more normal galaxies, we find them typically in this region here. Now, if I overplot these 10 systems that we've studied with ALMA initially, where they come out as here, and the 3 points are the ones where we have continuum detections, and then these orange points here are cases where we detect the C+ emission, but we do not detect the underlying continuum. So strictly speaking, we only have limits. But then when we stack these galaxies up, we get a stack detection of the continuum, and this blue point here indicates a stack of these 6 systems that are not detected in the continuum individually. And the interesting thing that we find is that these galaxies clearly lie above this cloud of points here in the nearby universe towards higher C+ to infrared ratios. So these galaxies appear to have enhanced C+ emission compared to the dust obscured star formation activity. And this is something that's very interesting, but it can have essentially a range of reasons, and I'm just listing a few of them here. So one possible origin is that essentially these could be galaxies that have low metallicities and therefore lower dust content. And essentially what happens if you have less dust is that essentially you have lower attenuation, and therefore you have a larger UV heating zone. And essentially the UV heating zone or the UV radiation field is something that scales with the strength of the C+ line, and this size is something that can therefore lead to an enhancement of the C+ emission. Now, another possibility could be that the dust temperature in these systems is low, so essentially that these galaxies might have considerable dust masses, but that the infrared luminosity might be lower than expected because the dust temperatures in themselves are lower. This is something that, as I'm going to show, will be disfavored, but in principle it's a possibility. And then lastly, it could be that these galaxies have unusually low star formation rate surface densities, and this is something that would lead to a less intense infrared radiation field, and ultimately would also lead to an effect like the one that's observed here. So these are possibilities, but how can we distinguish between them? And of course, the way that we do this is that we can carry out more observations. In particular, along this theme, what we can do is we can target more of these fine structure lines to see what they can deliver in terms of additional information. And the first thing that we did is that we targeted, in addition to the C+ line, we targeted the N+ line, so single ionized nitrogen line, at 205 micron in a subsample of these galaxies. Now, this line is interesting for several reasons, but one of the reasons is that the C+ emission can come both from neutral gas and ionized gas, because the ionizing potential of carbon is lower than that of hydrogen. However, for nitrogen, it's the opposite, so the ionizing potential, or the ionizing energy needed to produce N+ is higher than that of hydrogen. So essentially we only see it from the H2 regions around massive stars, and essentially from the ionized gas phase overall. So they trace different phases of the ISM, and therefore combining information from both of these two lines, we can learn more about the origin of the C+ emission, and therefore what might be driving this difference that we see in the interstellar medium properties. So what I'm showing you here is 3 galaxies that span almost 2 orders of magnitude and star formation rate is indicated here. These 2 are L star UV Lyman break galaxies, so 2 of the ones I've shown you before. Here's an example of a dusty starburst, and what I'm showing you here is the C+ line. And again, the impression I want to give you is that the C+ is strongly detected, but also that this guy here, which stands out in star formation activity, is actually not that much brighter in the line due to the fact that the scaling happens, then this very extreme systems, the line can be suppressed. And then what I show here in comparison is the measurement that we did in N+, and what you can see immediately is that this is a much harder measurement to do because this line is much fainter than the C+ line. But again, with ALMA, it's something that's possible. So essentially we get 2 detections here at about 5 to 6 sigma level, and we see some blip here at 2 sigma level, which is not really a detection, but it's a hint of a signal that we can also use in the interpretation. So essentially by combining these 2 lines, then we can try to learn something more about the interstellar medium properties. And this is what we're doing here. So what this plot here shows now is, again, on this axis the Farnsworth luminosity, but then on this axis here it shows the ratio between the C+ and N+ luminosity in galaxies. Now, this is again interesting because it tells us something about the physical properties, in particular if you do modeling with, for example, the cloudy code. What we learn is that a high C+ to N+ ratio happens in cases where we have high density or high radiation intensities. Because what happens in these cases is that essentially in these cases, we reach a higher ionization state of the gas, and therefore we can get less C+ emission from the ionized gas, and therefore a higher fraction of it from the neutral gas, and therefore you see both less C+ and N+ from the ionized phase, and therefore it's dominated by the neutral contribution of the C+ line, and this is why the ratio goes up. And you see then, of course, the opposite in the other direction. So essentially, if you sit down here, it means that you have a high contribution to the C+ emission from the ionized gas phase. Now, what we can see is that there's a bunch of points on here that I want to emphasize for a bit. And what we see in this region here is essentially all of these very extreme dusty starbursts and also quasar-host galaxies that we see here that have very high star formation rates and that are very extreme systems. And we see that they have some scatter, but by and large, they have relatively similar ratios in these lines. And then what we see here is one of these more normal Lyman break galaxies, but the one that has the highest infrared luminosity, so it's essentially the dustiest of these normal galaxies that we observed. And you can see that essentially it has the same ratio in these lines. So this is something that tells us, because we know that the conditions for star formation in these systems are greatly different, tells us that probably much of the N+ emission that we're seeing is actually coming from the diffuse ionized phase and not essentially from the H2 regions or the massive stars that are directly in the star-forming regions, because we would expect differences if that would be the case, because these are very different systems. And this tells us that essentially this ratio is probably not driven mainly by things like the star formation rate surface density. However, then probably the most interesting part is these points up here, which are the other measurements of the Farnsworth faint of these normal galaxies, where we see that the ratios are clearly elevated. So this is the log scale. So you can see that these points are clearly much higher than anything down there, despite the large uncertainties that we still have of these measurements, because the N+ line is very faint. And indeed, the only systems in the nearby universe that have ratios as high as this are local metal-poor dwarf galaxies. So essentially in these galaxies we find line ratios that are comparable to low metallicity dwarfs, even though these are normal, relatively large and highly star-forming galaxies compared to dwarf galaxies in the nearby universe. So they're different entities, but they look similar at these high redshifts because probably of their lower metallicities. Now, how can we piece this together? So one thing that we can then look is we can look at these nearby dwarfs and see how different properties scale with this line ratio. So I'm plotting up here as the same line ratio, C+ over N+, but I'm plotting it up here against the Farnsworth color, which essentially is an indication of the dust temperature. And we can see that there's not a very strong trend with the dust temperature, but there's a strong stratification in this direction here. And this is essentially indicated by the color coding, because the color coding essentially indicates metallicity. So the things that have lower metallicity have higher ratios than the things that have higher metallicities, and there's this trend with metallicity. Now, the reason why we think this is associated with the ionization state in the H2 regions is that in these lines, in these galaxies, we have also measurements of other species, for example, O3, so essentially in a high ionization state of oxygen. And we see that at the same time where we get the high C+ to N+ ratios, we also get an even higher enhancements in the O3 emission compared to N+, and also compared to C+. And this is why we get to this interpretation that probably this enhancement is due to the fact that the gas in the H2 regions is ionized to a higher state. So essentially we see less emission from N+, and also from C+ in these regions. And therefore that is a strong trend with metallicity, so you have less dust, and therefore less shielding, and therefore you reach high ionization in the H2 regions of these high redshift galaxies. And just to finish up, this is the last thing that I want to show. We get actually a consistent picture if you look at the CO emission, because I've indicated before that it's very hard to detect CO at this very high redshift due to the metallicity effects. But this doesn't mean that we can't try. And essentially, we tried for these two galaxies here, which again have the same L-star luminosity, but they have a significant difference in the dust-obscured star formation rates between them. So they look the same in the UV. They're both kind of main sequence normal galaxies, but one of them is much more dusty than the other. And these are essentially, again, the C+ and N+ lines for the two, just with a little more data than we had on the original paper. And these are the CO measurements that we get after long integrations with the VLA. And indeed, we are successful in detecting CO in this Redshift almost 6 main sequence galaxy, which is exciting because it hasn't been done before. But we do not get a detection in this guy here down to similar or even a little bit deeper levels. And this is again consistent with the idea that there might be a change in the conversion factor, the alpha CO, with metallicity, and that this guy here that shows less infrared emission has a lower metallicity than this galaxy here, and that metallicity is probably the main driver behind this change in the interstellar medium properties. Okay, I'm just going to leave out my summary slide. So I've convinced you that it's interesting to look at the interstellar medium in high redshift galaxies, and particularly to do this kind of integrated and total measurement through this CO deep fields to constrain the CO luminosity function and therefore the gas density of the universe, which then helps us to understand the driver of the cosmic star formation history. Then I've also described that hopefully we have a telescope by the 2030s, the NGVLA, that will be able to do this much better than we can do it at the moment, of course. And then lastly, CO is something that's difficult to use at the highest redshifts. That's why we're using other tracers, in particular these fine structure lines for typical galaxies out to redshifts of 5 and 6, and even higher redshifts by now with new measurements that are coming out. And based on doing these measurements, we see that there's a clear difference in the interstellar medium properties for these highest redshift normal galaxies, and probably what we're seeing is a strong scaling with metallicity in the interstellar medium properties. Okay, so this is what I have, so I'm happy to take questions now. Thank you.
Questions for Dominik? Giovanni.
Dominik, for the C2 observations, it equals 5 to 6 galaxies with ALMA. Did you have accurate enough redshifts on those that you fit into the ALMA bandwidth, or how did you do that?
Yeah. Let me just go back to the slide. So essentially, for all of these, we had spectroscopic redshifts from KEC. But actually having just Lyman alpha redshift would not have been enough. We essentially selected systems that also have absorption lines detected, which means that we have a much better redshift estimate than Lyman alpha alone.
And they were good enough that you could fit into the ALMA bandwidth?
Yeah, because of the absorption lines. From Lyman alpha alone, it would have been a bit of a gamble, but from the absorption lines, essentially get a good enough redshift that fits at those redshifts.
Okay. It did require KEC to get that,
Yeah, so these are like many out of KEC spectra. This is just a stacked one of all 10 of them. Okay. But yeah, to see the absorption lines makes big loss.
Okay,
So I was wondering about these, because you detected all 10 of these at
Yes.
redshift 5 and 6. How much further can you go in redshift?
So with this last line,
assuming they're either roughly the same or, yeah.
So assuming that you have galaxies with some metallicity out there, essentially there's no reason why it has to stop at redshift 7, 8, even 10. Okay. So you should be able to do this to much higher redshift in principle. And I think the main limitation will be that eventually galaxies will run out of metals, and once you have zero metallicity, there's no C+ anymore because there's no carbon. Yeah. But it can, in principle, drive this much further. And there's now some detections that are a bit higher beyond redshift of 6. And there's even an O3 detection now that's beyond redshift of 7. So essentially we're getting out there.
Go on, yeah.
Just keep going.
Yeah. Okay. Go ahead.
Since we know that the metallicities of galaxies are evolving, and you're suggesting that there might be a dependence of alpha CO on metallicity, how large of an impact can this have on your results related to, let's say, the density of CO in the first part of the stuff?
Yeah, that's a good question. And this essentially goes back to the tracing from the CO luminosity function to the H2 density. And indeed, one other possible explanation is that if the conversion factor would be different than what we think it is, it would explain why we get the right gas mass measurement, or where you get the gas mass measurement, the gas mass density measurement that's consistent with the model for a luminosity function that's very different. So it's another way that we could reconcile this is if there would be a difference in scale with conversion factor. That being said, we're trying to get better constraints on this by getting additional information on these CO galaxies. The first thing we're trying to do is to resolve them and get dynamical masses to set more direct constraints on the conversion factor. But then for the ones that optically bright, hopefully we can also do deep optical spectroscopy to get other kinds of diagnostic lines for metallicity beyond what we have so far. So there's more work to be done. Yeah.
Yeah, you had these objects where you had a confirmed redshift because you had more than one line, but no optical infrared counterpart.
Yes.
Is that just obscuration by dust, or is it really amazing?
It's first of all, it's observation by dust, which is not amazing.
That's not very amazing.
Yeah, so essentially the ones that we don't see at all in the optical, they are essentially in the redshift 5 bin, so they see CO2 to 1, so they're both far away and they're extremely obscured. So those are the ones where the dust is just all in front of us. And actually some of them we do see pop up in the IRAC bands, they just drop out in K-band or something like that. But they start to come up in the IRAC bands, but there's one that's not even detected in IRAC.
So that's one of your JW proposals.
Exactly, yeah. So these are the things that JW would be great at.
What about H1? We find that in NGC 2207, which is a nearby galaxy involved in a grazing encounter, that if you look at the higher star formation regions in it, they are H1 dominated, and that if you include the H1 plus the molecular gas produced from CO, then you get the normal Ketterkichman relation. But if you don't include the H1, then we don't get it. And these are areas where you have high turbulence in the gas, and that alters the structure of the clouds.
Yeah, that's actually interesting because in those regions, again, another thing that could be going on is that the CO conversion factor might be wrong, right? Because you have high enough turbulence, then actually the mass of these clouds might also be enhanced compared to what you expect, which would throw off your conversion factor as well, right? So this thing can also play a role, but I agree, I mean, the H1, ideally we would have that information as well to be sure that we take all the gas phase into account. Promise at high redshift, of course, we can't detect H1 at the moment in galaxies. Yeah. No, but I mean, this is a good point.
Change the subject completely.
Yes.
You invited this question and I'm going to pose it. Namely, what more can you tell us about the next generation VLA?
Yes, I'll be happy to talk more about it. So it's a concept study that's going on, and I would say has been seriously going on for a couple of months, essentially mostly this year, that a lot of more progress has been made. So right now there's a conceptual design that exists for the telescope that's driven by some science cases that have been proposed. So essentially there's of order 70 science cases that have been developed for the NGVLA, and there will be a science book written up later this year that hopefully comes out by late 2018 on the science cases. But what the telescope design actually is that it will be an array telescope that has of order, I think 214 antennas is at the moment what is being anticipated, with baselines going out to of order 300 to 500 kilometers. And the idea is it's centered in New Mexico, but then essentially goes all the way to Texas and to Mexico down. So it's a huge thing.
The Southwest Telescope.
The Southwest array.
These are going to be connected elements?
Yeah, so it's going to be acting as an interferometer. So it has kind of a compact core to essentially get surface bias sensitivity, and then these arms that go out to long baselines.
Electrically connected, not like VLBI.
Yeah, so they're all connected. Supposed to be connected, so there will be a lot of cable that we have to run to do that. And then we'll operate essentially from 1 to 115 gigahertz, essentially going from H1 to CO in the nearby universe is kind of sets the scale. So essentially it includes 3 millimeters, which turns out the VLA side is relatively good at doing, even though it's not being done for anything but VLBI at the moment. But there's a lot of weather that can be done. And at the moment, the design is that this range is split up into 6 bands. So essentially, you have in each band you have a very large bandwidth or large fractional bandwidth to essentially realize it. But yeah, going up all the way between H1 and 3 millimeters.
And what's the rough estimate of cost?
So people have floated that it's of order an ALMA in $20, $30-something. You can take that as one. So I don't know, $2 billion.
Like a space mission.
Oh wait, it's on YouTube. I don't know if I should those numbers.
Given that you're looking at these high Z's and you think that the metallicity is really getting low relative to solar, does that affect the calibration of the infrared derived star formation rates?
Yeah, that's a good question, because it can influence it both to the fact that the dust composition might be changing, and therefore the way things trace might be changing. The other thing that might be changing is that these galaxies might actually have a different dust temperature. I've alluded to the fact that some people proposed these might have lower dust temperature, but actually the indication that we seem to be getting is that the dust temperatures of these normal things are higher than we expect. So essentially they have hotter dust in them, it's less dust, but essentially the dust has a higher temperature, and that's also why they faint in the infrared at the wavelength when we're trying to detect them. This is still tentative at the moment, but this is kind of what the indications have been. And therefore, of course, if it's hotter dust but not more dust mass, but you can see whether or not there's indication that there's really more star formation going on. Yeah, so there might also be an issue with the calibrations of
Could
the
you
dust.
test it by looking at the sort of UV-derived star formation rates and comparing them? Because the UV should be more accurate if there's less extinction.
If there's less extinction, the UV is more accurate, and in principle, I didn't show this today, but in principle there's an indication that this might be the case, because there's this relation is often used to determine extinction. It's called the IRX beta relation, looking essentially at the infrared axis compared to the UV continuum slope. And initially it seemed that these galaxies are far off where they should be in this diagram, but it would be reconcilable if they would have higher dust temperatures and therefore higher infrared luminosities with nothing else changing. But still, if we would be able to do this adjustment, essentially where they would come up is essentially in the region where again we find low metallicity galaxies like the SMC, not where we find normal spiral galaxies, the first order. Yeah. But yeah, there's an indication for that from that side as well.
In your picture of the NGVLA, it looks a lot like the Paul Allen telescope. So I take it the dishes are sort of 8-meter sized instead of so the individual elements are more Paul Allen telescope size instead of VLA size, and you have a larger field of view, and I guess this is all driven by the much cheaper electronics in the correlator.
Yeah, so essentially there's a trade-off between UV coverage and sensitivity and field of view, right? So that's kind of the trade space I worked in. So essentially these antennas are supposed to be 17 meter, that's the latest, and then with that there's 214 of them. So they're smaller than the VLA, but not a lot smaller. And in principle for these deep field studies, of course we like smaller telescope because of the larger field of view. You're more efficient at doing surveys, but also, as you said, it gets harder to correlate the signal if you kind of have to introduce more antennas to keep the same collecting area. So it's that trade-off space. Yeah, but essentially because there's a few hundred of them, the idea is that they need to be cheap each. And that's what's driving part of the design. So they need to be cheap, but also they need to be cheap to maintain because they're spread all over the southern US, right? So you can't drive out there every day with a truck and try to fix something. Once you have that many and have them spread out that much. Yeah, but this is kind of the latest design that people came up with. I don't know if that is the final design. That's kind of that trade space, having cheap antennas that are easy to maintain, that are still precise enough to do this.
This be in New Mexico also?
The whole southwest
Yes.
covering with these.
Yeah, so the core will be New Mexico, which will be like 40-50% of the collecting area. They will be sitting close to each other, and then have long arms to go over to Texas and down to Mexico.
Wow.
Yeah.
That's the idea.
Wow.
It's huge, yeah.
Relations with Mexico will be improved.
Yeah, it's actually.
So we can immigrate there?
We can build a few of them on the wall.
Yes. Any last questions?
Right.
Okay, otherwise let's thank Dominik again.